Alright guys, welcome to lesson 9 of unit 3. We're going to talk about infinite limits today and limits at infinity. And this time we're going to use something called L'Hopital's rule. So by the end of the day, you should be able to evaluate a limit of some functions at infinity. And then you guys should be able to use L'Hopital's rule to evaluate a limit. You should also be able to tell me when you're even allowed to use L'Hopital's rule, because you're only allowed to use it in certain conditions. And actually, the way that we write our work when using L'Hopital's rule matters. So we want to make sure you know how to accurately express your work. So once again, we're finding limits at infinity, primarily focusing on L'Hopital's rule, when you're allowed to use it, and how to write it. All right, so let's go ahead and start by looking at this particular limit here. Now, I want to approach infinity, positive infinity, and I also want to approach negative infinity for this function. Now, the n just means that this number could be any integer you want to. It could be 1 or 2 or 3. So long as, well, actually, we should probably say positive integers. So it could be like 1 over x squared or 1 over x cubed. It doesn't really matter. We're going to get a similar result anyway. I think for the purposes of this problem, I think I just did 1 over x to the first power. But let's go ahead and just pretend for a second that the n is a 1. So I'm just going to go ahead and erase the n really quick. So what is the limit of this function as x approaches infinity? Now, you can't ever reach infinity, but you could approach infinity by plugging in bigger and bigger numbers. So let's go ahead and start by plugging something in. The first thing I want to plug in is 0. So I want to plug 0 in for x. Now, you're not allowed to, right? If you plug 0 in for x on the bottom, you're going to get an undefined expression because you can't have 0 in the denominator. But let's go ahead and plug in another value for x. Let's plug in 1. Now, if I plug in 1, I'm going to get, and then I want to plug in a bigger number. Let's try 10. And then a bigger number, and a bigger number, and a bigger number. Now, that's how we approach infinity, is by plugging in bigger and bigger numbers. All right? So let's go ahead and see what we get. If we plug in 1, you're going to have 1 over 1, which is 1. If you plug in 10, you're going to have 1/10, which can be written like that as a decimal. If you plug in 100, you get 1/100th. If you plug in 1,000, you get 1/1000th. And if you plug in 10,000, you get 1/10,000th. So that's what we seem to be having here. So as x is getting bigger and bigger and bigger, in other words, as x approaches infinity, what does the y value seem to be approaching? It seems to be approaching 0, doesn't it? It's getting smaller and smaller and smaller and closer to 0 the bigger that x gets. Let's go ahead and see what happens as I approach negative infinity now. So same thing, only now I'm going to plug in numbers that are negative. So like -1, -10, -100, -1000, and -10,000. I was supposed to have a negative on that 100 there. I made a boo-boo. All right. So anyway, so we're going to plug in those values now and see what we get. So if you plug in -1 for x, you're going to get -1. If you plug in -10, you get -1/10. -100 gives you -1.01, and so on. Well, the same thing's happening. We're still as x is approaching negative infinity, my y value is still approaching 0. So it doesn't matter whether you're going to positive infinity or negative infinity. The reality is the limit of this function as x approaches either infinity is 0. Okay? And so that's a limit at infinity, and the limit of this function at infinity is 0. This is a pretty useful little thing to be aware of, and we're going to use that here and there throughout our lessons. So here we go. Now, let's talk about evaluating expressions at infinity. So let me ask you a question here. If you take infinity and you multiply it by a number, a positive number, what are you going to get? You're going to get infinity, right? You can't get, so I mean, if you take an infinitely big thing and you multiply it by a number, you're still going to get infinity, even if you multiply it by a number. Well, what if you take negative infinity and multiply it by a number? Well, now you still get negative infinity. So it doesn't matter when you're dealing with infinity. If you multiply it by a positive number, it just stays exactly what it is, because infinity means infinity, and there's nothing bigger than infinity. All right, so let's go ahead and take a look at another one now. What if I take my positive or negative infinity and multiply it by a negative number? Well, that's just going to reverse it. So in other words, if it's positive infinity, it's going to become negative infinity. And if it's negative infinity, it's going to become positive infinity. So it just reverses it. I don't like how I wrote that. Write it like that. That way it's the opposite of this, right? So if you multiply infinity by a negative number, it's still infinity, but it does change the signs. Okay? Let's take a look at another concept here. Now, this is not multiplication anymore. This is addition or subtraction. I just want you guys to be aware of that. So, if you take positive infinity and you add a number to it, what do you get? You get infinity. And if you take infinity, positive infinity, and you subtract a number from it, what do you get? You still get positive infinity. It doesn't really matter. If you take infinity and add or take something away from it, you still have infinity. It doesn't change it. Infinity is a weird thing, isn't it? Infinity means forever. It's not like a normal number. In fact, it's not a number at all. What happens, though, if we take negative infinity, and I add a number to it? Is it going to change it? Nope. It's still going to be negative infinity. What if I take negative infinity and I subtract a number from it? It's still going to be negative infinity. So my point here with this problem is that if you have positive or negative infinity, no matter what you add or subtract to it, you're still going to have positive or negative infinity. So it's a lot like the multiplication one that we had earlier. If you multiply infinity by a positive number, you just get the same answer. If you take positive or negative infinity and you add or subtract a number from it, you just get the same answer. But something does different if you multiply by a negative number. That's different, so we want to keep that in mind. Let's go ahead and take a look at another one here. What's infinity plus infinity? It's just infinity. All right. How about negative infinity minus infinity? Well, that's going to be negative infinity. You just took negative infinity and you took infinity away from it, so you just get more negative infinity. How about this one? What if you take infinity and you divide it by a number? Well, if you take something that's infinitely large and you cut it in half, guess what you got? More infinity. Doesn't matter. Because infinity is always infinity, whether you multiply or divide it. Okay? Because it goes on forever. If you cut forever in half, you just get another forever, because forever is forever, right? All right. Let's see what else we got here. Oop, I'm a little bit off the screen. Let me see if I can lower this a little bit. There we go. All right, now here's an interesting one. Now this one actually is not. This one is not obvious, so we need to talk about it. What happens if you take a number and you divide it by infinity? Well, guys, that's just another way of saying this, which we talked about on our last slide. If you're plugging in bigger and bigger and bigger numbers to the bottom, to the point where basically you just end up plugging in something extremely large, what did that become? It became 0. So for this one, the answer is 0. All right, what's next? Now, if you multiply a positive infinity by a positive infinity, you get infinity. Or if you multiply negative infinity by negative infinity, you still get a positive infinity. It doesn't matter so long as they're the same, right? But what happens if you multiply positive or negative infinity by its opposite? So like, let's say you did positive infinity times negative infinity, or negative infinity times positive. Well, then you're going to get negative infinity. It's just like numbers, right? When you multiply a positive times a negative, you get a negative. If you multiply two negatives or two positives, you get a positive. Now that's all I'm going to discuss. There's some other things that we haven't talked about yet. Like, for instance, what happens when you do infinity minus infinity? Believe it or not, you guys might be inclined to say it's 0, and it's not. So we'll talk about that later. But for now, we have all of our answers that we need to work on this. So This is something that I included in your guys' flashcards in the back of your notes handout for at the beginning of the year. They're on the flashcards, and I would encourage you guys to use them just to kind of be ready, because a lot of times you're going to need to know these little facts in order to properly evaluate limits at infinity. So now I'm gonna treat this like direct substitution. Okay, so I'm going to put this, I'm just going to plug infinity in. Now what is positive infinity when you multiply it by a negative number? It's negative infinity, because we talked about in the last slide how if you multiply infinity by a negative number, it just changes its sign, right? How about the next one? Let's do direct substitution. What's infinity squared? Well, infinity squared, that just means infinity times infinity, which we talked about in the last slide. That just means infinity. All right, let's do the next one here. Here we've got negative 2 over infinity cubed. Now this is actually a two-step problem. Okay, so first of all, infinity cubed, that just means infinity times infinity times infinity, which is infinity. But after we do that, now we have negative 2 over infinity. We talked about this. When you have a number on the top and infinity on the bottom, that one actually is the weird one. That turns out to be 0. That's like taking a limit of 1 over x as x approaches infinity, and you get 0. Okay, let's do the next one. Here we're going to have infinity squared plus 2 times infinity minus 1. Okay. Well, we've already done this earlier. That's just infinity. We've done infinity times a number. We know that's infinity. And then we have minus 1, which we'll just bring it over. We know that infinity plus infinity is infinity. And we also know that infinity minus 1 is infinity. So the final answer there is infinity. Infinity's weird, isn't it? All right, let's go ahead and take a look at another one. Clear this board up. It's a little crowded. All right, so let's do our direct substitution again. So that's going to give me 3 minus infinity. Okay? It might be helpful if we rewrite this a little bit. Think of that as negative infinity plus 3. It's the same thing. Okay? Just moving the numbers around. Put the positive 3 in the back and the minus infinity in the front. And now it makes a little more sense. So if you take negative infinity and you add a number to it, it doesn't change it at all. So you actually just are left with negative infinity. All right, let's go ahead and take a look at number 6. Now we've already talked about this one. If you plug in infinity there, you get infinity. We've already talked about that. You're just going to get infinity. This is interesting. Let's talk about that in a second. All right. We've already talked about this too. That's just infinity. So I'm going to continue my work up here. So these two just become infinity. And then we still have the 1 over. Now what's infinity plus 2? Well, that's just infinity, right? All right. Now we have this. What does this equal? Well, anytime you have a number over infinity, it's just 0. We don't really care about 0. You just get rid of it. What's infinity plus 5? It's infinity. All right. So there you guys go. That's evaluating limits at infinity. Okay. Let's go ahead and let you guys practice some of these. Here's a couple for you. So go ahead and pause the video, work these out, see how many of them you can get correct. When you unpause the video, you'll see the solution. All right, so there you guys go. I'll let you check your work there. Answer number 1 is negative infinity. Answer number 2 is 0. And the answer number 3 is just negative infinity. Okay, let's go ahead and move on with our lesson here. Now these are what we call indeterminate forms. These are things where we can't really say for sure what the answer is. Okay? Now let's talk about that, because believe it or not, there are different kinds of infinities. And Even though they both go on forever, the fact of the matter is some infinities are actually bigger than other infinities. So I mean, for instance, think about this. Think about between the number 1 and 0. How many numbers are between 1 and 0? There's an infinite number of numbers between there. You can cut it in half. You can say, okay, well, there's a half. You can cut it into fourths and find the fourths. But you can keep cutting everything in half, and you can never stop. You'll never find the total number of values between 1 and 0. So technically, there's an infinite number of numbers between 0 and 1. But you guys, what if I ask you how many numbers between 0 and 2? Well, guess what? There's infinite there as well. But you could tell by the distance between those two numbers that one of those is bigger than the other one, right? So that's really weird to think about. It kind of makes your brain twist around and hurt a little bit. But there it is. Infinite numbers, there's different kinds of infinities out there, and some infinities are bigger than others. So now whenever I tell you take infinity and you add an infinity to it, these don't have to be the same. The point is you're taking something that's infinitely large and adding it to something else that's infinitely large. Even if that other one is bigger or smaller than the other infinitely large thing, they still end up with an infinitely large thing, right? But we have a little bit of problem here, for instance. If you take infinity and you subtract infinity, if these two infinities are not the exact same kinds of infinities, you're not going to get 0. Because one infinity could be different from the other. So you may not end up with 0. And this is what we would call an indeterminate form. We can't really know what the answer is to this. Okay? So all of these are indeterminate forms. If you divide infinity by infinity, we're not really sure. Here's another one. You can't have 0 over 0, because we talked about that before. You're not allowed to have 0 in the denominator anyway, right? That's an indeterminate form. Or 0 times infinity. That's not allowed either. Infinity minus infinity, we don't know what that is. We can't tell for sure. Infinity to the 0 power, 0 to the 0 power, 0 to the infinity, and 1 to the infinity. Now, honestly, we don't really care about almost any of these, because I'm not going to require you guys to study those almost at all. There might be some extra credit questions that I'll make up for you guys and we'll go through maybe. But really, these are the two we need to focus on. These are the two special kinds of indeterminate forms that we need to focus on. So let's go ahead and see what we're going to do with all these things. The reason why we care about this is because it has something to do with L'Hopital's rule. All right, now L'Hopital's rule is probably the coolest limit finding rule there is, because it literally works on almost any kind of limit you want to find. So we've learned a lot of other types of limit things, but this one actually kind of works on everything. I've only been able to find one type of problem that it doesn't really work very well on, but it pretty much solves every other limit problem there is. So I like to talk about it last. The other ones have good value for what they're worth, but this one works on almost everything. So let's go ahead and take a look at it. So suppose you're trying to find the limit of some kind of an expression that consists of a fraction like this. But when you do your direct substitution, you either end up with 0 over 0 or you end up with infinity over infinity. The signs don't matter. If you end up with one of those two indeterminate forms, then you're allowed to do L'Hopital's rule. Now here's what L'Hopital's rule says. It says the limit which you're trying to find is equal to the limit of the derivative of the top over the derivative of the bottom. Okay? And a lot of times after you take the derivative, guess what? You're able to go ahead and just do direct substitution after that and get an answer. So it's pretty interesting. So the first time you try to do direct substitution, you get an indeterminate form, but then you take the derivative of the top and bottom and then you plug in and you get an answer. It's pretty interesting. Why does that work? We're not going to learn why this works. We're just going to use it. The proof for this is very intense and completely unnecessary for the purposes of our class, so we're going to leave that alone. We're just going to use it, and we're going to use it quite often. It's very helpful. All right, let's go ahead and get started here. I'm going to change that. I don't like the way that looks right now. It's supposed to be a power of 2. There we go. Looks better. All right, so let's go ahead and evaluate each limit. So the first thing I'm going to do is I'm going to do my direct substitution of my limit here. So I'm going to plug in infinity. And I end up with infinity over infinity. Now, just so you guys know, this is kind of like a lame little rule, and when I learned this, I had to keep myself from rolling my eyes whenever I learned about this. But on your FRQs, don't put equals here. And the reason for that is because this is an indeterminate form. And an indeterminate form is not a number. So you can't say that your limit is equal to something that's not a number. Now, you know, I'm just thinking of this kind of like we go from here to here to here. So maybe arrows would be okay. I don't think they would have a problem with that. But we do end up with an indeterminate form. But don't put equals, okay? If you do that, you will lose points. And I wish they didn't do that, but they actually did. They actually had a student who, on the FRQs one year, they actually did the entire problem right, but because they put equals, they actually took their point off, and I thought that was really sad. So I'll just tell you guys to avoid that so that way it doesn't happen to you, okay? Okay, so we get an indeterminate form. Now, since I got an indeterminate form, I don't have an answer. But that doesn't mean there isn't an answer. So now what I can do is I can say, by L'Hopital's rule, we could say that the limit as x approaches infinity of 3x squared over 5x squared minus 3x minus 1 is equal to the limit as x approaches infinity, negative infinity, of the derivative of these things. So what's the derivative of 3x squared? That would be 6x. What's the derivative of the bottom? That would be 10x minus 3. Okay? So now let's go ahead and see if we get an answer. So I'm going to plug in my infinity, and I end up with 6 times infinity over 10 times, and I better be careful with my equal signs, because if I get another indeterminate form, we can't have that there. So I'm going to erase that for now. 10 times infinity minus 3, which is infinity over infinity minus 3, which is, we still have infinity over infinity. So we still don't have an answer. Now sometimes that will happen where you need to do L'Hopital again. So I still got an indeterminate form. Every time I get an indeterminate form, we're going to do L'Hopital's rule again. So since the limit as x approached negative infinity of 6x over 10x minus 3 was an indeterminate form of infinity over infinity, that means this limit is equivalent to the limit of its derivatives of the top and bottom instead. So what's the derivative of the top? It's 6. And what's the derivative of the bottom? It's 10. All right. Well, now there's nowhere for me to plug this infinity in, and that's because this is a constant function. And so no matter how far off we go into infinity, it's always going to be 6/10, and so the answer is 6/10, which reduces to 3/5. And so we actually do end up with an answer. Okay. Now we also, let's see, have we learned about probability? No, we haven't learned about those yet, so we'll leave it at that. But anyway, 3/5 is the answer. So what's the process we go through here? Let's reiterate it. First of all, you do direct substitution, and be careful, use arrows because you could end up with an indeterminate form. We don't want to put equal sign. And if the arrows give you one of the indeterminate forms of infinity over infinity or 0 over 0, then by L'Hopital's rule, we could say the original limit we were trying to find is equal to this, which would be the derivatives. And a lot of times you have your answer at this point, But sometimes you got to keep going. So like on this problem, we got another indeterminate form, so we had to go again. So that limit would be equal to the derivative of that one. And then finally we get 3/5. And that's L'Hopital's rule. Now, there's a lot of writing up here. But basically, you guys, I'm going to try to make it a little bit simpler to understand. If you get infinity over infinity, take the derivative and plug it in again. If you get infinity over infinity, take the derivative again and plug it in. But I think what's important to show is that remember how we said how you write your answer matters? You need to say that it's indeterminate, and then you can say what we have here. And then we had to say it's indeterminate again, so we had to say what we had here. And then you could just write your final answer. So I would say what we have written here, this is all the important stuff to write. If I plug it in, I get an indeterminate form. So by L'Hopital, this limit equals this limit. But when I plug it in, I get another indeterminate form. So now I can say this limit equals this limit. And with this one, I actually get an answer of 3/5 is my final answer. Okay? So you don't have to show everything that I showed, but you do have to show that it becomes indeterminate. And remember not to put equals. And then you have to show that the limits are equal and find the answer. So let's do another one. Here we go. So for this one, we're not plugging in infinity. You'll notice we're plugging in 1. So if I plug in 1, I'm going to get 1 squared minus 2 times 1 plus 1 over 1 minus 1. Now that's going to give me 1 minus 2 is negative 1 plus 1 is 0. And I just put an equal sign again, darn it. Gotta be careful with that. And I've got an indeterminate form, and that's a L'Hopital indeterminate form. So therefore, that's the symbol for therefore, by the way. By L'Hopital's rule, the limit as x approaches 1 of our original function is equal to the limit as x approaches 1 of this new function, which is going to be the derivative of the top over the derivative of the bottom. And now we go ahead and do some direct substitution. And we end up with 0 as an answer. Okay? And notice I have equal signs here, and that's okay, because now I don't have an indeterminate form. You're not allowed to have anything be equal to an indeterminate form. But if you come out with a number, you can have the equal signs. All right? So there it is. Do your direct substitution. If you get an indeterminate form, by L'Hopital's rule, write out the L'Hopital statement, and then do direct substitution. Let's do one more. All right. So by direct substitution, I get up a little bit here. I end up with 1 minus 1 over 1 plus 1, which is 0 over 2. Is that an indeterminate form? No, that's actually an answer. So I'm going to put equals now. So this one, I just kind of threw it up there just so you guys don't get too trigger happy and start thinking that, oh, well, we're always going to do L'Hopital. You're not. This one was actually just a very straightforward direct substitution problem. We didn't need to use L'Hopital's rule. We could find the limit simply by direct substitution. You only do L'Hopital's rule if you end up with infinity over infinity or 0 over 0. So let's go ahead and see how you guys do with applying L'Hopital's rule here. Go ahead and see if you guys can evaluate the limits for these two functions. When you unpause the video, you will see the solutions. All right, guys, so here's our solutions. And what I have here is the bare minimum of the amount of work that you guys should be showing on these problems. So remember, we want to know not only how to do L'Hopital's, but when can you do L'Hopital's. So let's answer those. When can you do L'Hopital's? You could do it anytime you have this or this. Okay? How? Well, basically, it's just derivative over derivative with direct substitution. But how do you write it was another thing that's important. And that's what I'm writing here. We want to make sure that we're using arrows instead of equal signs when you have this or this. And we also want to make sure that we're saying that the original limit is equal to the new limit with the derivatives in it, right? So anyway, I'll go ahead and talk my way through the problem now in case you guys had any questions of any kind. So first of all, by direct substitution, we get an indeterminate form. Therefore, by L'Hospital's rule, the limit of the original function is equal to the limit of this new function, which is the derivative of the top and the derivative of the bottom put together. But once again, direct substitution gives me another indeterminate form, so we do L'Hospital again. So by L'Hospital's rule, the limit of that new function, we take the derivative of the top and bottom and create the limit of a new function, which is going to be 2 over 4. And since that's just a constant function, it's always going to be 2/4, and therefore the answer is 1/2, which is the reduced form of 2/4. Now for number 2, this one, it yields the indeterminate form. So by L'Hospital's, the limit of the original function is equal to the limit where you have the derivative of the top over the derivative of the bottom. This time, if we do direct substitution, I do not get an indeterminate form. I just get infinity. Now you guys will notice that I put arrows instead of equal signs. I don't think it's really technically right, although they didn't say this to me. But I don't think it's technically right to put equals infinity either, because infinity is not a number. You can't equal infinity. You can approach infinity. So I think arrows will be a good way to go with this particular problem. But there you guys have it. So the answer to number 2 then is just basically infinity, because infinity over 1 is infinity. All right. Now I think that can, well, let's see, we have a little bit more here to do today. Here we go. Here's a shortcut for finding limits of rational expressions at infinity. Okay, now this is really kind of overwhelming to look at. So let me give you guys something a little simpler to look at. What I mean is basically you have a polynomial of some kind over some other polynomial. Okay, it's got to be a polynomial. In other words, you can't have square roots, you can't have natural logs in there or trig functions. It's just got to be a straight up polynomial. Okay, so I'm about ready to give you guys a shortcut, which I think you'll really appreciate, but it's something you just got to commit to memory. Okay, so if you're taking the limit of a rational expression, meaning polynomial over polynomial, as x approaches positive or negative infinity, I wrote that a little bit incorrectly. It should be this. As x approaches positive or negative infinity, then we have a really neat little shortcut. Here it is. If the biggest power on the top is smaller than the biggest power on the bottom, the limit will always be 0. So for instance, if I gave you guys this, and you wanted to find the limit of that as x approached either positive infinity or negative infinity, it has to come out to be 0. It has to be 0, because this power is less than this power. Okay? But what about another situation? Let's suppose that they're equal. We actually saw this happen on our last slides in the sample problems that we just finished. Let's say that they had the same power, like x to the 4th over 3x to the 4th. Well, in that case, if they're equal, then we have another shortcut. The shortcut is basically you're going to take the number in front of that one and the number in front of that one, and that's your answer. It just always works out that way. And you guys can kind of see that happening as on the last few examples that we were looking at. Now there's one case up here you'll notice that we didn't talk about, and that's what if the power in the top is bigger? Well, in that case you're going to get some kind of infinity as an answer, which once again we saw that on the last one as well. That was your number 2 on the last page. That one, the power in the top was greater than the power in the bottom, so we ended up with an infinity as an answer. But for that one, I don't have a shortcut for you guys to give as an answer, because it could be positive or negative infinity. And it's kind of complicated trying to narrow it down which one it's going to be. So for that one, I'd say just go ahead and do it old school way and you'll be fine. All right, so let's go ahead and take a look at example 3 here. So first of all, we want to identify the problems below for which we can actually even use that shortcut. Okay, so let's go ahead and find where we can do the shortcut. Anytime the power on the top is less than the bottom or equal to the bottom, we can do it. So I could do that here, because in this case, 1 is less than 2. And I can do it here, because in this case, 2 is equal to 2. I can't do it here, though, because the power on the top is bigger than the bottom, and I can't do it here either for the same reason. We would have to do these ones using L'Hospital's rule, the old school way. But for these two over here, we've got a nice little shortcut. We talked about this one. Whenever the power on the top is less than the power on the bottom, the answer is just 0 because we're approaching infinity. And by the way, that's another detail you want to watch out for. If I had a number here instead, then this rule doesn't apply. You've got to do it old school style. It only works if you're approaching infinity. All right, here's another one here. Now we are approaching an infinity here. So for this one, since the number on the top and the number on the bottom is the same, you're going to take this number and you're going to put it over this number, and that negative has to stay there also. So the final answer here is going to be negative 2 over 1, which is just negative 2. So it's a nice little shortcut, and you're definitely welcome to use it. That way you don't have to show all your work and spend so long on trying to do L'Hospital and everything. Let's go ahead and have you guys try some of these. So see if you guys can find out which one of these you're allowed to do the shortcut on, and then do the shortcut. I'll pause the video here, and then when you unpause it, you will see the solution. Oops, let me bring it back there. All right, so neither one of the ones on the top could have the rule applied. I wish I would have put a better example up here, but this one here doesn't apply for two reasons. One is because the power on the top is bigger than the power on the bottom, but also because there's a negative 1 here. It has to be approaching infinity. This one here doesn't work just for one reason, though. It's because the power on top is bigger than the power on the bottom. Now, they work on the bottom here. So for this one, since the power on top is less than the power on the bottom, it equals 0. And for this one, since the power on top is equal to the power on the bottom, it's just the ratio of their coefficients. So negative 3 over 1, which is negative 3. The example I wish I would have put up here would have been one that looks like this. Let me back up a little bit. Okay, well, there's no x on the top at all, first of all. That's not a problem, though, because you could put one there. It's just x to the 0. And yeah, the power on the top is less than the top, so you might be tempted to say, oh, it equals 0. But no, because it's not approaching infinity. So you got to watch out for stuff like that. Okay, but so long as you are, in fact, approaching infinity, and the power on the top is either equal to or less than the power on the bottom, then you can do the shortcut. All right? Other than that, that's where we'll call it a day, and we'll wish you guys well until the next lesson.